This year, a quantum chip did in minutes what the fastest supercomputer on Earth would need longer than the age of the universe to finish. A robot beat a human world record over 21 kilometers. And an AI didn't just help design a drug, it got that drug into a real human clinical trial, with real published results. These aren't predictions, and they aren't concept demos buried in a research paper nobody read. They already happened, this year, and most people haven't heard about a single one of them. Stick around, because by the end of this video, you'll understand exactly why the very last breakthrough on this list should worry you a little. 2026 has been the year two separate revolutions: artificial intelligence and quantum computing stopped being lab experiments and started rewriting what's actually possible, on timelines that are catching even the experts off guard. We went through everything published, announced, and peer-reviewed this year and ranked the 15 breakthroughs that matter most, not the loudest headlines, the ones that actually change what's possible next. Let's start at 15. In April, a fully autonomous humanoid robot named Lightning entered the Beijing E-Town Half Marathon and won. Its time, 50 minutes and 26 seconds, nearly 7 minutes faster than the human world record over the same distance. No remote control, no human pacing it from the sidelines, the robot planned its own gait, balance, and pacing in real time over more than 21 kilometers of real, unpredictable city streets, with turns, camber, and crowds. Just 2 years ago, a humanoid robot walking steadily on a treadmill was the headline. Now it's outrunning elite human athletes on an actual course. That gap closed faster than almost anyone in robotics predicted. For years, AI drug discovery mostly meant AI helping human chemists narrow down which molecules to test faster. That changed this year. A compound called rentasertib, developed by In Silico Medicine's generative AI platform, became the first drug where both the biological target and the molecule itself were designed by AI, and it completed a phase 2 human clinical trial with published, peer-reviewed results. It hasn't received regulatory approval yet, and it may still fail later trials, most drugs do. But it proves something the entire industry has been chasing for a decade: an AI-originated drug can survive contact with real human biology, not just a simulation. That single result is why 2026 is being called the year AI stopped being optional in drug discovery. Bigger has always meant better in AI, more parameters, more compute, better results. That's been the rule since the beginning of the deep learning era. A genomics model called GPNstar just broke that rule. At 200 million parameters, it outperformed a rival model with 40 billion parameters, 200 times larger, at predicting how cells respond to drugs and genetic changes. A companion model, MSIPerformer, did something similar for protein structure prediction. It means the next leap in AI for science tools might not come from bigger data centers and bigger budgets. It might come from smarter architecture that smaller labs can actually afford to build. In emergency rooms this year, AI systems started catching brain hemorrhages in scans within seconds, before a radiologist could even visually confirm them on screen. In a stroke or a traumatic injury, every minute of delay costs measurable brain tissue, and it's often the single biggest factor in long-term recovery. This isn't AI replacing doctors, it's AI acting as an always-on triage system, flagging the one scan out of 100 that needs eyes on it immediately instead of in 20 minutes when it gets to the top of the queue. Hospitals piloting this technology are already reporting measurably faster treatment starts, which in stroke care translates directly into outcomes. Quantum information is famously fragile. A quantum state collapses the moment it's disturbed by, essentially, anything, including just being measured. This year, researchers extended how long a quantum state can survive inside rare earth crystals out to tens of milliseconds, a 200-fold range boost for quantum communication links compared to where the field stood before. That doesn't sound dramatic until you realize what it actually enables: linking separate quantum computers together into one larger network system, the same basic idea that turned isolated computers into the internet decades ago. No single quantum computer has to do all the work alone anymore. Here's a distinction that matters more than almost any other number in quantum computing: A physical qubit is fragile and error-prone on its own. A logical qubit is built from a group of physical qubits working together to actually detect and correct their own errors as they happen. In March, Quantinuum announced 94 logical qubits running on their H-series processor, one of the largest error-corrected quantum systems ever demonstrated in public. A few years ago, research teams were celebrating getting a small handful of logical qubits to survive at all for any meaningful amount of time. 94, holding stable, is a genuinely different era of hardware. Microsoft's Majorana 1 chip is built on something genuinely strange, topological qubits, based on a particle first predicted mathematically in 1937 but never definitively confirmed in this engineered form until Microsoft's own research this decade, a particle that is theoretically its own antiparticle. The pitch is that topological qubits are inherently more stable than the qubit types every other major lab is using, which means dramatically less error correction overhead is needed to keep them working. Microsoft is betting this approach gets to practical, fault-tolerant quantum computing in years, not decades. It's the most unconventional bet in the entire quantum race right now, and if the physics holds up at scale, it could leapfrog competitors who bet on more established, but more error-hungry, approaches. IBM's newest processor, Nighthawk, delivered a 10 times speedup in error correction over its predecessor, a full year ahead of IBM's own public schedule. Combined with their 1,000-plus qubit Condor chip, which came with meaningfully improved coherence times and lower error rates, IBM now says it's on track to demonstrate verified quantum advantage, a real task a quantum computer can solve that no classical supercomputer can realistically match, no matter how much time you give it, by the end of this year. That's not a research promise buried in a white paper anymore. That's a company with a stock price putting an actual date on the calendar. The International Mathematical Olympiad is one of the toughest math competitions on the planet, the kind of problems that stump most working mathematicians, let alone the general public. This year, AI systems from both OpenAI and Google DeepMind solved 5 out of 6 problems under actual competition conditions, working in natural language, earning scores at gold medal level. Not by searching a database of known solutions. By reasoning step by step through genuinely novel problems that no model had ever seen before, the same way a human competitor would. 3 years ago, AI chatbots could barely do reliable multi-digit arithmetic without a calculator plugged in. Now they're medaling against the best teenage mathematicians on Earth. Most AI models that claim to watch video are secretly cheating, quietly converting it to a text transcript first, which throws away almost all of the actual visual nuance, timing, and motion. Google's Gemini 3.1 Ultra processes video natively at 60 frames per second, reasoning about what's actually happening as it happens, with no transcription shortcut in the pipeline. Meanwhile, its sibling model, Gemini 3.1 Pro, more than doubled its score on ArcAGI2, a benchmark specifically designed to resist memorization and test genuine novel problem-solving instead. Put those two things together, real-time visual understanding plus real reasoning underneath it, and you get the foundation for things like live safety monitoring, real-time coaching, or assistive tech that actually sees the world instead of just chatting about it. Historically, AI models specialized. One model was best at coding, a different one was best at creative writing, another was best at reasoning, and you picked your tool based on the specific task in front of you. OpenAI's GPT 5.4 broke that pattern this spring, credibly leading across coding, computer use, reasoning, and general knowledge work all at the same time, inside a single model, rather than a specialized lineup. For anyone actually building products on top of these systems, that's a bigger deal than it sounds. Fewer trade-offs to manage, fewer specialized tools duct taped together behind the scenes, just one capable model doing most of the job. This might be the quietest breakthrough on this list, and the one that changes the most jobs. Anthropic's Claude Sonnet 5 shipped this summer with a full 1 million token context window as standard, and critically, it doesn't just answer questions when prompted, it independently reads an entire unfamiliar code base, plans a multi-step set of changes across dozens of files, runs its own tests, and fixes its own failures, without needing a human to walk it through each step. That's the shift from AI as a chatbot you talk to AI as an autonomous coworker you assign a task to and check on later. It's already scoring ahead of previous top-tier models on real-world software engineering benchmarks, not just conversational ones. For decades, the working assumption in quantum computing was brutal: the bigger and more complex you build the machine, the more errors accumulate, and the harder it gets to trust any answer it gives you. This year, that assumption broke, on the record, in multiple independent labs. Researchers confirmed that logical error rates now decrease exponentially as quantum systems scale up, the exact opposite of what used to happen as recently as a couple of years ago. Experts are calling it the dividing line between the old noisy era of quantum computing and the new fault-tolerant era. It's arguably the single result that made every roadmap on this list, IBM's, Google's, Quantinuum's, Microsoft's, suddenly look like realistic engineering timelines instead of hopeful marketing slides. Google's Willow chip became the first quantum processor to demonstrate error correction below threshold, meaning, exactly like breakthrough number 3, it gets more reliable, not less, the bigger you scale it. But the headline result out of Willow is almost hard to say out loud without pausing. It ran a real physics calculation, called the out-of-order time correlator algorithm, roughly 13,000 times faster than the best classical supercomputers currently on Earth, finishing in a few minutes what those supercomputers would need longer than the current age of the universe to complete. This is the closest anyone has come yet to an undeniable, independently verifiable demonstration that quantum computers aren't just a different kind of fast. For the right category of problem, they're categorically faster, in a way classical computers structurally cannot catch up to by adding more chips. Here's why we ranked this above even Willow's 13,000 times speedup. Everything on this list has technically been happening on two separate tracks: AI getting smarter, and quantum computers getting more powerful and more reliable. Individually, each one is exciting. Put them on the same timeline, and the math changes. Modern encryption, the kind protecting your bank account, your medical records, your private messages, basically the entire digital economy, is secure specifically because classical computers can't factor extremely large numbers fast enough to break it in any useful amount of time. Quantum computers, at large enough scale with good enough error correction, mathematically can. None of that is new information. Cryptographers have known this for over 25 years. What's new, as of this year, is how fast the timeline is shrinking, now that error correction is scaling exponentially in the right direction instead of the wrong one, on multiple competing hardware platforms at once. Governments already know this. It's exactly why new encryption standards specifically built to resist quantum attacks were finalized and are now actively being rolled out across banking and government systems. The breakthroughs on this list aren't just cool tech demos. Some of them are a countdown, and the clock started before most people even knew it was running. That's 15 breakthroughs, from a robot breaking a marathon world record to a quantum chip outrunning the laws of classical computing, with a genuine encryption countdown sitting quietly underneath all of it. If even one of these surprised you, it's probably going to matter to your life sooner than you'd expect. Tell me in the comments which one you think is the biggest deal, and which one you think is overhyped. I read every one. And if you want to actually understand what's coming next instead of just reacting to the headlines after everyone else, subscribe. This is exactly what we break down here, every single week.